Okay, let's start. Today we are going to continue to talk about reinforcement learning. So in the last lecture, we talked about Q learning and policy iteration. The idea was to basically characterize either the Q function or the V function using neural networks. And then by computing the argmax of the Q over different actions, we can compute the policy in order to see in what actions we should take in different states. But as I mentioned last time, we have thought about different optimization problems in either supervised learning or unsupervised learning, and majority of them we have tried to approximately solve it using gradient descent or different variations of it. So the question is, can we use gradient descent in order to tackle the reinforcement learning problem? And that's going to be the main goal of today's lecture. So our goal is to basically solve this optimization, right? So you have a value function that tells you what is the expected reward if you start at a particular state, depending on the policy that you are following, policy pi, and we want to maximize this over different policies. Can we take gradient descent in order to solve this optimization problem? Can we use gradient descent to optimize over pi? All right, what do you guys think? I have this optimization problem. I want to maximize the value function. Let's say starting at a particular state S. Is it possible that I just take the gradient of this function with respect to pi based on the stuff we have learned so far? Or what are the potential bottlenecks? Any ideas? Okay, so I have a couple of responses. It says if pi is differentiable. Another response is or domain for pi may not be continuous. Very good. D-dimensional, if we need pi to map discrete states to actions. I think all of them are answers in the right direction. Right? So the answer is yes, we can, but we need to parameterize the pi function, because if you're thinking about a discrete mapping from your discrete states to discrete actions, then that function is not going to be differentiable. So we need to come up with a function for pi that is nice and differentiable. So the answer is yes, in fact, we can. But we need to parameterize the pi function. Okay, and during this course, we have learned one good choice for parameterizing functions would be to use deep neural networks. So we are going to use neural networks in order to do that. Remember, in the last lecture, we used neural networks to parameterize either Q function or the V function. Here, it is a little bit different. Here, we are using neural networks to parameterize the pi function. So my pi function, let's say, would be a function with parameters theta, mapping my states to my actions. So if I want to have a picture, let's say at time t, you are in state st. So you have a neural network. And at the end of the day, you are getting an action A of t. And here the action can be a discrete action, or it can actually be a continuous action. So I'll talk about some examples of it later on today. So that's going to be your policy function, pi theta. It gives me an action A sub t given the input S sub t where I'm at particular state. Now I have this action, then it's going to go to my environment with the transition probabilities that we don't know. Then I'm going to end up in another state. It's t plus 1, and this loop continues. So I start, let's say, in a state S1, I take a particular action A1, I go to another state. Depending on the transition probabilities in my environment, then my policy tells me to take another action, so on and so forth. And here we are going to, for simplicity, we are going to consider the finite horizon case when we have t steps. So because of that, we actually don't need to worry about the discount factor. So this whole thing I'm going to refer to as a trajectory. With tau, I mean like a sequence of states and actions. So one note I want to make here is that here the policy function depends on the state. But in some applications, you may have partial observations. And in those cases, then your policy function would input that observation and then output your action. I just want to make that remark here. In partial observation case, pi theta would be a function mapping observations to actions. So if you're interested, you can look at the literature for this, but we are not going to covering partial observation case today. Okay, so let me pause and see if there are questions so far. So if not, let's move on. Now I want to compute probability of observing a particular trajectory. Okay, so I give you a particular trajectory tau, and I want to see what is the probability that this trajectory is being observed using a model depending on the policy pi sub theta and the environment, the transition probabilities coming from the environment. So that's the probability I'm going to show with p sub theta of tau. That's the probability of observing a particular trajectory. So the initial state is just like the probability of being in that state, p of s1. And then I'm taking a particular action using the policy network. Let's say I am in state S sub t, and my policy tells me to take this particular action with this probability. So that's the probability of taking action A sub t given I'm at state S sub t. And after I take that action, my environment is going to take me to a new state, st plus 1, given that state and the action that I have taken. Now, since we are assuming we are still in a Markov case, so these probabilities are going to be multiplied to each other from 1 to t. So therefore, the probability of observing a particular trajectory is the probability of S1 times probability of take a particular action A1 given S1. And then after I took that action, my environment is going to take me with some probability to S2. And then I'll basically repeat this process. That will be the probability of observing a particular trajectory. Okay. What about the reward function? Let's say I have a particular trajectory, S1 goes to A1. I take an action A1, goes to S2, so on and so forth. And here we are going to consider reward is a function of state and action. So I have these rewards, and my ultimate goal is to maximize the total reward that I'm collecting. And here I'm considering the finite horizon case. So I'm not considering any discount factor, but you can easily add a discount factor. Okay, so the total reward for a particular trajectory, let's say tau 1. So I realize this trajectory tau 1. So I'm going to sum up the rewards that I'm collecting. Let's say I started in state S1. My policy told me to take an action A1. Then my environment using S1 and A1 took me to S2. So I have reward S2, A2 up until the last reward that I consider. That's the reward. It's a single number. It tells me how good this trajectory is. If it is bigger, I'm happier. If it is smaller, I'm less happy. Okay. Now let's say I have, for a given policy, what are the randomness I have in generating a trajectory? Right? I have some randomness because of my policy function. There's a randomness for a given state, what is the action I want to take, and also there is randomness coming from my environment. So these are two sources of randomness in a particular trajectory. Let's say I run my simulator and I generate different trajectories. Say I have a particular trajectory, let's say tau 1. Again, by this I mean there is like S1 going to S2 by an action A1, and then I took another action A2, so on and so forth. Let's say I generate another trajectory from my simulator, and I repeat this many times. Tau 3, so on and so forth. As for each of them, I'm collecting the reward. The reward associated with this particular trajectory, this is the reward associated with tau 2, it's the reward associated with tau 3. And at the end of the day, I'm going to evaluate the quality of my policy network by averaging these rewards over different realizations of these trajectories. Because at the end of the day, the reward associated to a trajectory is a random variable, because trajectory itself is a random variable. The randomness comes, of course, from the environment, but also from the policy network that we have. So I'm going to look at the average of these rewards, and that will be a single number associated to a policy network to evaluate its quality. Higher that number, better for me. So if I look at the average reward, let's call that with J of theta, because theta is my model parameters. That is defined as the expected reward of different trajectories when these trajectories, of course, are generated by P sub theta. That is the average reward function associated for a particular model parameter theta. So therefore, my goal would be to pick theta to maximize this. I want to find parameters for my policy network to maximize this particular objective function, J of theta. Okay, so there is another way to compute the average reward, and that is by, so here for each trajectory, remember R is sum up all of these rewards. So I get this reward. I sum up basically row wise, and then at the end of the day, I look at the average over different trajectories. Another way would be to look at the average rewards for each pair of state and action and then sum them up, right? So either you look at the sum in rows and then you average the rewards associated to each trajectory, or you can look at the average reward for each state action pair and then sum them up. So that's another way, and you'll see sometimes it is useful to go between these two formulations. So in order to do that, we need to look at the marginal distribution of P sub theta on this particular state action pair. In fact, this picture is a little bit not clear. So here we just consider a particular state and action pair, another state and action pair. So I look at the marginal distribution of P theta of a trajectory. So P theta is basically the probability of observing this really long sequence. So I'm going to marginalize it over S1A1, S2A2, and that's going to be my marginal distribution. I call it with P sub theta S1A1. It's going to be P sub theta S2A2, so on and so forth. And I can use these marginal distributions in order to compute the average rewards for that particular state action pair. Average reward for this particular pair would be expectation of the reward at S1A1 if S1A1 is distributed according to P theta S1A1. Same thing for this. So in other words, this J of theta not only can be computed by looking at the rewards for each trajectory, I sum up row wise and then I look at the average column wise. I can look at the expectation for each state action pairs and then sum them up. So it is going to also be equal to sum from T1 to T, the expectation of the rewards I have in each state action pair. And here STAT is distributed according to that marginal distribution. And it is a useful formulation. Sometimes we start with the first one, but sometimes it is easier to use the second formulation. But nevertheless, my objective here is to find the theta to maximize the average reward associated with that particular model. Okay, I see there are some questions. Let me pause here. Is the network retrained per each iteration from scratch, or do we retrain on top of the previous network? So hold on a second. So I haven't even talked about what is my training. So far I have just talked about what is my objective function. And my objective function is to pick theta, my model parameter, characterizing policy function to maximize the average reward, J of theta. So we'll see how we can solve this optimization. Is there an upper bound on the number of trajectories in the marginal distribution for calculating J's of theta? So that's a great question. So hold on that thought. So I'll talk about that in a minute. Any other questions? Is the formulation clear? So that's the main question I have for you guys. Okay, good. So let's move on. Is there a question? Okay, if not, let's move on. Okay, now we are going to just use gradient descent to solve this maximization, or gradient ascent, right? Because we are doing this maximization. That's the whole idea of today's lecture. Use gradient ascent to solve the maximization. So in order to use gradient descent or ascent, I need to be able to compute the gradient of my objective function with respect to the parameters. So let's do that. What is the gradient of J of theta with respect to model parameters? All right, so I'm going to use the first definition for now, the gradient of the expected reward associated to each trajectory when my trajectories are distributed according to pi sub theta. And let's assume the trajectories are in a continuous domain. Similar argument for a discrete case as well. Then this expectation can be written as an integration. Right? So I have a density function, p theta of tau, times the reward associated to that trajectory, d tau. And integration is linear, so the gradient will get into the integral. So I'll have gradient of p sub theta of tau times the reward associated to that trajectory, p sub tau. Okay. So let's stare a little bit at this gradient. So what is the dimensionality of this guy? Gradient of p sub theta of tau. Is it a scalar? Is it a vector? Same dimension as theta, that is correct, right? So theta is like the set of my model parameters. I may have like hundreds or thousands or even millions of parameters. So it's like a really huge vector. It's in a high dimensional case. And I need to compute this integration. So how can I do that? Like, even what I'm asking is, how can I even approximate this integration? Because like my space is huge. Like there's a suggestion, saying we can use MCMC, but how can I even take samples? Like my tau is going to be in a really, really huge space. How can I take samples in order to even approximate this integral? So I hoped to have some sort of expectation, right? So if I don't have it, but if this integral was in a form like, let's say I have p theta of tau times a function of theta times r tau d tau, then I would be happier because I could write this as the expectation over p theta of whatever this function is times r tau. And then I could generate some random samples from this expectation. So this would be my approximation. I would maybe generate n samples and then approximate this expectation with n samples, right? But the issue here is that I don't have p theta of tau outside of the gradient. So that's the problem here. But interestingly, here algebra comes to our help. In fact, you can easily show that this gradient of p sub theta is actually equal to p sub theta of tau times the gradient of the log of p sub theta. In fact, it is not even an approximation, it is equality. And because this is the case, then I can write this integral as this expectation, and I can take n samples in order to approximate this integral. Let's say I look at sample I, the ith trajectory I generate, and I'll just look at this empirical average in order to do approximation of this integral. This is the key idea of the policy gradient algorithm. So that's it. That's the whole idea. So I see there are some questions. Can we assume P sub theta's family of functions? Yeah, you may come up with some other ways in order to compute this integral, but here I wanted to write this integral as an expectation over P sub theta, and then be able to compute that with some approximations. Remember, J of theta itself is an expectation, right? So we have no problem about that in order to compute it. But the problem is that can I write the gradient of J of theta with respect to theta also as an expectation? And the answer is yes. So the gradient of P sub theta is in fact equal to P sub theta times the gradient of like a log of P theta. I really don't care about this function. So what I care is to have this P sub theta outside so I can write this integral as an expectation. So why this is the case? So let me actually show a one-line proof for star, proof of star. So let's actually start from the right-hand side. If I look at P sub theta times gradient of log of P sub theta, gradient of the log function is the gradient of the input over divided by the input, right? So I have the gradient of P sub theta divided by P sub theta. And as you can see, immediately these two cancels out. So gradient of P sub theta is equal to P sub theta times gradient of the log of P sub theta. And that's the key algebraic observation that we use in order to turn that integration into like a nice expectation, so I can approximate that using some samples. Any questions? Okay, if not, actually let's do this calculation. Now I have like this expectation of this gradient of log of P sub theta. Let's actually see what can be even further simplify it. Now I know P sub theta of a trajectory is according to this formula that we have before. Right? So that's the formula for probability of a particular trajectory. So let me rewrite that here. So I have probability of S1. And I have, with this probability, I'm going to, I'm taking another action. And here's the transition probability to another state. Now I wanna compute the gradient of the log of this function. So let's first take the log. So I have log of PS1. The log of multiplication would be the summation of the logs. And again, I have a multiplication, so I have a summation of the logs. Okay, now let's look at the gradient, because at the end of the day, I want to look at the gradient of the log function. All right, so does the first term depend on theta or not? No, so it doesn't depend on theta, so I have 0 here. What about this term? Does it depend on theta? Not, right? Because it's the environment, so it has nothing to do with my policy. So my gradient, therefore, is it's like sum of the t gradient terms of log of my policy network. That's it. So therefore, if I plug this, let's call this 1. So now I have a kind of an easier formula for the gradient of the log of P sub theta using 2. Then if I use 1 and 2 together, I have this really nice formula for the gradient of my average reward function, which would be an expectation over tau. I generate samples. So the first term is the gradient of the pi of theta, which will be according to this formula. So I have gradient of log of, actually I have a sum from 1 to t, gradient of log of P sub theta, a t given st, times what? Times the reward, which is again the sum of the rewards that we get in different pairs. So I'll also write that up as a summation over t1 to t R, ST, and AT. And that's it. That's the objective function. That's the gradient that we have. And as I mentioned, the reason that we wanted to write this as an expectation, because now I can take n samples from it. If I have a simulator, so I have n samples. These are different trajectories I generate, 1 to n. Now I'm going to approximate this expectation with empirical average over those n samples. So that would be, the first time is like T1 to T, gradient log pi theta, AT of trajectory I, ST of trajectory I. So I'll look at these values for a particular trajectory, and I look at the empirical average. ST for a particular trajectory I, and AT for a particular trajectory. And that's it. That's the policy gradient method. Just to summarize, so I generate n trajectories. Tau 1 to tau n. Then I compute the gradient, approximate the gradient of J of theta according to this formula that we have. Very easy because of like backprop, I can just easily compute all of these gradient terms. And then I'm going to update my model parameters using gradient ascent because I'm maximizing. Right? So it could be theta plus my learning rate alpha times gradient of J sub theta. Start with some random theta, answering Amir's question, start from scratch, random theta, and then use gradient ascent in order to do the optimization. So this is a really, really simple deep reinforcement learning algorithm and very powerful. In fact, you can easily implement it in different scenarios. Let me pause here and see if there are any questions. Okay, so we have about like 20-25 minutes left because at the end I want to talk a little bit about the final as well. So let me see. Okay, so let's first, I think it is important. So let's build some intuition about the policy gradient algorithm, and I'll see if I'll have some examples for that. So let's start with the intuition. Okay, so here, what I'm maximizing, I'm looking at the objective in this form. Right? So I have the log of the probabilities for a particular trajectory multiplied by the reward function. So that is the basically the objective that we started from. Right? So that is the gradient updates that we have. Eventually, that is used in order to optimize my average reward, which is just the expectation of the rewards that we have. Now, what that says is that now if you have different trajectories, let's say you generate tau 1 here, you generate another trajectory, tau 2. So let's say the reward that you get here is large and the reward that you get in another trajectory is low. Therefore, the gradients that you are going to, the gradients are multiplied by the rewards. larger the reward associated to that trajectory is, the contribution of the gradient, that gradient to your model update is going to be larger, because it is it's a weighted average. So in other words, it's like a try and error. So we generate these trajectories, and then the ones that are good, we are increasing their probabilities by weighting the gradients of the model with respect to them by the associated reward. So therefore, we increase the chance of observing better trajectories overall. So that's kind of formalizing try and error. So by the way, there are some really nice visualizations of it in a tutorial by Finn and Levin in ICML, I think 2018 or 19, about reinforcement learning. So that's a good resource to, in general, for understanding different aspects of deep reinforcement learning. And they have some good visualizations for this as well. Okay. So I'm going to skip the example I have for the policy gradient. And I'm going to talk about some of the issues that we face in policy gradient. For the example, again, you can refer to this tutorial by Chelsea, Finn, and Levin in ICML. So let's talk about some issues about policy gradient. It's a really simple and powerful method, but there are some issues that we need to be aware of and also take care of it. So the first issue is coming from this step, right? So we are approximating an expectation with an empirical expectation. And one of you asked this question, okay, so how many samples do we need in order to have a good approximation? So in general, we may actually have a really high variance of the gradient estimation. The estimator is unbiased. Of course, if n, the number of trajectories you have, goes to infinity, it will converge to the actual expectation, but we may suffer from having a high variance in gradient estimations. So again, as I mentioned, the gradient of the loss, the objective function that we have, we wrote that exactly as an expectation using the trick of the gradient of the log probabilities times the reward. So far so good. But here we have this expectation, right? So we look at the empirical average over n samples. Please unmute yourself if you're not asking a question. So here we may have high variance. So even like, just to get a feeling about it, if I add some constant number to all of my rewards, so all of these rewards are going to be a really big one, potentially all positive numbers. And it shouldn't change my problem, but having large reward numbers will contribute to having larger variances when we are looking at the finite n. And n can actually increase with the magnitudes of the rewards functions that we have. So that's one issue contributing to observing high variance of these gradient estimations in practice, that if we add a constant with respect to, of course, theta, right, to all of the rewards, the problem is the same. but we get higher variance in estimating in gradient estimations. Okay, so that's a practical issue that we face in the policy gradient method. So there are two kind of solutions try to, in a heuristic fashion, try to reduce the variance of the gradient estimation. I think there may be some better methods in the future, but I'll explain these two solutions, partial solutions. These are based on really nice intuitions, and they in fact help in practice, but still we may suffer from high variance even with these solutions. So one solution to reduce the variance, as I mentioned, one reason we may have a high variance is that you can add a constant to all of these rewards. So the idea is that can we like somehow subtract some numbers from these rewards, like to have them like zero mean in a way, and then we won't deal with this issue of adding a constant. So even if that's the case, that will be subtracted out. So that's the first solution, to subtract the baseline. And the idea is that now, if I rewrite my gradient of the objective function, again, it's an expectation over taus that I generate using our model of gradient of the log probabilities. Can I actually, instead of reward, can I subtract a constant with respect to theta? This constant may depend on the states, I don't care, but the constant is a constant with respect to theta. Can I subtract it from the rewards? And in fact, the answer is yes. So you can subtract a constant from the reward. So as long as B does not depend on theta. And the reason is really simple, because if you look at the expectation of the gradient of your log times B, you can easily show that expectation is in fact zero. So it really doesn't change your gradient calculation. So one good choice in practice is just to generate n trajectories, look at their associated rewards, and just like have this be as the average of those rewards, so subtract it from those n rewards that you have to make them zero mean. So in that case, my B would be just like average of the n rewards that I observe from different trajectories that I have. So it's a good choice. It helps in practice to reduce the variance. So people also, they have looked into like non-constant rewards. If the reward is a function of theta, then you need to add some additional terms to make sure that it doesn't influence your expectation, because at the end of the day, we want to have an unbiased expectation. And people have looked into that, but this choice that I mentioned here, it is very simple and it helps in practice. Okay, so let me pause here and see if there is a question. There's a question, could you explain again why the intuition is higher, rewards gets higher probability? Right, so here your log probabilities are multiplied by the reward. So if the reward is higher, so the probabilities, the log probabilities, and log is a monotonically increasing function, therefore the probabilities will have a higher contribution to your gradient. In fact, you're changing your model to increase the probabilities of better trajectories compared to other trajectories. Any other questions? Okay, so as I mentioned, there are two main solutions to reduce the variance of the gradient estimation in practice. So the one was like just to subtract the base function. The second solution, it's a complementary solution in fact, is based on this following argument. Right, so let's look at again, the gradient of my objective function, and I'm approximating that using n trajectories that I generate. These are, I have log probabilities times the rewards. And we had like more detailed formulations of these terms based on the pairs of states and actions. So let me actually write them up, and that's something that we are going to use here. So for the log probabilities, if you remember, so the states and the transition probabilities doesn't depend on theta, so I can just look at the sum of the gradients of probabilities of my pi theta network over t times over trajectory I. And for the reward, I can actually also sum it up over pairs of states and actions and sum it up over different t's. Let's use another index t prime just to make sure it is not confused with t. Okay, so this is a scalar, this is a number, and these are vectors, right? So it's a gradient with respect to theta. The size of this vector is going to be the same as the size of my model parameters. So here I'm going to multiply this scalar with each of these t vectors and then sum them up. So here I sum up these t vectors and then I multiply with this number. Or alternatively, I can just multiply this number to each of these vectors and then sum them up. One to n. So I'm going to have sum from t1 to t. For each of these vectors I have the gradient terms. I'm going to multiply it with that particular number. Okay, so let's understand this a little bit better. So this is the gradient of my policy at time t. So if I'm at the state st for this particular trajectory, what is the output of my policy network? This is the gradient of that. I'm multiplying that to what? To the rewards I'm collecting, not from time t to capital T, from the beginning. Even if this gradient is computed in like time 5, then the number I'm multiplying it is from some of the rewards from 1 to capital T. Right? That's what it is. That's the formulation for my gradient. So people argue because of the causality of rewards for a particular trajectory, we can approximate this. Again, I keep these terms as is. Same term here. But for this, I'm going to sum up rewards from that particular T to capital T, instead of summing up the rewards from the beginning. So this is called reward to go, and often referred to as Q function. And remember, Q is basically a sum of the reward functions depending on a state and an action, right? And that's exactly one sample approximation of the Q function. At time t, that's why I'm going to put a Q hat, and that's one sample for a particular trajectory I. So it turns out using this approximation actually helps in practice. So that's these are like the two techniques, either like subtracting the baseline or using reward to go instead of like the total reward in order to improve the gradient estimation when you have finite number of samples. So that was like the first issue for the gradient, for the policy gradient method, that the approximation that we have for the gradient estimation can have high variance. Let me pause here and see if there are any questions. If not, let's carry on. So another issue about the policy gradient is that we are optimizing in the theta space, but some of the parameters can change the probabilities more than other parameters. And therefore, setting the learning rate, maybe a fixed number for all of the parameters, can be quite challenging in practice. Some parameters can change pi theta more than others. Therefore, it is hard to choose a fixed learning rate. So what can we do about it? So where does this first fixed learning rate actually came from? So if you look at like gradient descent or gradient ascent, let's say I have a loss function, I have an objective function j theta. So I'm at this particular model parameter theta, and I wanna follow my gradient, right? This is the gradient of j theta at this particular theta. I wanna follow my gradient, but by how much? So can you just like, you know, update your parameters theta with like, you know, 10 to the power 6 times this gradient vector? No, like we wanna like have smaller updates because we wanna also keep close, you know, the approximation gap where we end up and where our actual function is. So in other words, so in standard gradient ascent, we are solving this following objective, that I want to go in the direction of my gradient. I want to find the theta prime, which is in the direction of my gradient. That's why I maximize the inner product. But I don't want theta prime to be too far. So I want theta prime to be relatively close to theta. So I don't want to like, you know, have a really, really big distance between theta and theta prime. So this leads to my gradient ascent updates, that theta prime is theta plus, let's say, alpha times the gradient vector. All right, so instead of having a constraint on the L2 distance between theta and theta prime, maybe we can constrain the difference in the pi of theta and pi of theta prime. These are the probabilities. So maybe I can introduce like a probability distance measure between pi and theta of theta prime. That is the key idea for resolving the second issue. So instead, I'm going to again go in the direction, maximize theta minus theta prime with the direction of my gradient. But for instead of this constraint, I'm going to, let's say, maybe a divergence between pi of theta and pi of theta prime should be less or equal to epsilon. All right, there are many choices for this divergence. I'm not going to go into the details, but a popular choice is the KL divergence. And in fact, we can use approximation, a Taylor approximation of the KL divergence. That's the most popular one that people use in practice. If we use a Taylor approximation of the KL divergence here, this constraint can be simply written as theta prime minus theta transpose theta prime minus theta less or equal to epsilon. So if I didn't have any matrix here, it would be the same as my L2 constraint that I had before. But here I'm going to have a matrix called the Fisher information matrix. Fisher information matrix. And this matrix can be estimated using the samples that we generate. So this is called natural policy gradient. Okay, really simple, right? So you basically have, instead of the L2, you have the Fisher matrix. And in that case, your update actually becomes simply just like theta prime is theta plus, instead of just like multiplying with alpha, you're going to multiply alpha with the inverse Fisher matrix times your gradient. So that's the only difference that you have compared to the policy gradient. Okay. So just like to mention one other approach to improve policy gradient is based on this formulation that we have here. Right? So this is like a one sample estimation of the Q function. But in the previous lecture, we learned that actually maybe we can parameterize Q function by a neural network itself. So that's another way to reduce variance in the policy gradient. So those methods are called actor-critic algorithms. So here we'll have two networks, one for pi, that is the actor. So I have a pi sub theta, but I'm going to, like this, instead of like estimating Q with one sample, I'm going to have another neural network for either my V or my Q function, because I can compute Q using the V function. So that's basically the idea of the actor-critic algorithms. It's basically policy gradient, but for that, instead of the Q function, we use a neural network in order to have a better estimation. So again, your gradients can be written as some 1 to n, some t1 to t, gradients of the pi probabilities times the Q function is ti and ati. And remember, I can't subtract the baseline if it doesn't depend on theta, if it depends maybe just on states. And a good baseline is just a value function because it doesn't depend on A, it only depends on S. So I can do that. So this term is often referred to as the advantage function. It says, if you take an action A, compared to the average value you're going to get, what is the average reward that you're going to get? What is the advantage of taking this particular action? So this is the advantage function. But the learning is basically the same. So you represent V with like a neural network, you estimate Q, then you estimate this advantage function, you estimate your gradient, and you iterate in order to optimize your policy. And it reduces the variance of the gradient estimation significantly. So it's a really good algorithm. Okay, there are many other topics in reinforcement learning that I didn't cover. Other important topics in RL. Some of them I briefly explained before. One is like inverse RL, where you don't even have the reward function and you want to estimate your reward function maybe with some expertise that you have. There's like a really growing area of multi-agent RL where you don't have just one agent, you may have multiple agents, and maybe you are in a zero-sum game or maybe a collaborative game. We have also model-based RL that we characterize the transition probabilities, characterize the environment. So it is usually difficult, but for example, you can start with like some simple models. Let's say your next state is like a linear combination of your previous state, the action, and maybe like a Gaussian noise. So that may be like one model for the environment, but usually it is difficult to characterize the environment precisely. As I mentioned before, some of these other topics, more advanced topics, are covered in this ICML tutorial by Finn and Levin. And that's a good resource to study these topics a little bit further. All right, that is all I have for the reinforcement learning part. I'll pause here and see if there are any questions about the reinforcement learning stuff we covered today. And then I'm going to have a summary for the course, and then I'm going to take your questions about the final exam. Is everything clear? So we learned about Q learning, we learned about policy iteration, and we learned about policy gradient today. And we realized, okay, the approximations can be high variance. We talked about different ways of reducing the variance by subtracting the bias term, by representing the Q function or V function using a neural network itself. And by also looking at rewards to go. So these are some of the techniques that people use in practice, and they, work pretty decently.